Hey y'all, I'm here to talk to you about a topological approach to proving the fundamental theorem of algebra. Now, we all remember the fundamental theorem of algebra, right? A polynomial of degree n is greater than or equal to 1 with complex coefficients, has n complex roots, with multiplicity possibly greater than 1. So for example, consider this cubic polynomial that I just kind of cooked up. By inspection or by some other method maybe, we can find that it has roots of 5 and negative I. And actually, we can rewrite this polynomial as x minus 5 squared times x plus I. And in fact, this shows that it has exactly 3 roots, negative I with multiplicity 1 and 5 with multiplicity 2. Now, this seems maybe obvious, right? But it turns out one needs either some complex analysis or algebraic topology to really show this. Again, very wild that I know I was introduced to this in something like middle school, or at least a version. Today I'm going to be using the latter to rigorously prove this theorem. So I'm going to make some simplifying assumptions first. First, we're going to presume that our polynomial is monotonic. That is, it takes this form here. Of course, if it's not, f of x is of this form here with an not equal to 0. But since the complex numbers are a field, we can rewrite this as a sub n times g of x, with g of x being this different monotonic polynomial. And any roots of f of x are roots of g of x, so it has n roots if and only if the monotonic g of x has n roots, and so we can just look at the monotonic case. Additionally, let's presume that a naught is non-zero, because if it's not, then we have f of x of this form. We see that 0 is a root by inspection, and from there we can just kind of skip to the last part of our proof, which I'm excited to get to. But first, we got to talk about homotopy. So what is homotopy? Homotopy applies to paths on a topological space. And if two paths are homotopic, then we can continuously stretch one path into the other. So for example, take these two paths right here. Are they homotopic in the complex numbers? I encourage you to pause the video to figure it out. Great, now that you're back, yeah, absolutely these are homotopic. You could totally stretch these into each other continuously. However, are these two paths homotopic in the punctured plane? That is, the complex plane, but without the point 0, with a hole there. Can we do that? Again, feel free to pause the video if you'd like. That's right, they can't be homotopic there, because, again, you would have to somehow get around that hole, which you can't do. So how are we using this idea? Well, we're going to consider the images of two different paths, right? We've got this little gamma. Again, both of these paths are from the interval 0, 1 to the complex numbers. Little gamma is defined as such, and big gamma is defined as such very similarly. We note that these are two circles that are homotopic, right? In Desmos, you can just kind of graph these as circles. Pretty clear. We can also consider, though, the image of f, right? Since it's homotopic to itself in the complex numbers, then the images of f composed with little gamma and f composed with big gamma are homotopic to each other. This is just a theorem from topology, algebraic topology. This is what it might look like, these paths, if you had this particular polynomial, for example. But are these always homotopic in the punctured plane? That's what's going to be really important for our eventual proof here. So I'm going to give a general structure of this proof. I'm following a proof from Matthew Steed, who you'll be able to see the URL to it later. You can also probably find it if you just search up Proofs of the Fundamental Theorem of Algebra. It's the UChicago one. But I'm going to skip over a couple of details. I encourage you to look at his original work. The details I'm going to skip over also are things that are mostly triangle inequality, actually, so stuff that you don't need a bunch of topology background to understand. And if you don't understand it, of course, you can always just look that up, or if you don't want to understand it because you're on break. What we'll do is we'll show that any polynomial first has just one root, right? Then by an inductive argument, then we can say it has exactly n roots. We'll show that it has at least one root through contradiction, right? If it doesn't, then the image of f does not include 0, and thus it's continuous in the punctured plane. So you've got these two paths that are homotopic to each other. Now, I'm going to define two functions here, right? g1 of x is equal to 1, and g2 of x is equal to e to the 2 pi I n x. N is, of course, the degree of our polynomial here. And then we find that f composed with little gamma and f composed with big gamma are homotopic and nowhere 0, so therefore homotopic in the punctured plane to these two other paths. This is the part with the triangle inequalities that I'm not going to go over actually, just for the sake of time. But then we're going to show that these two paths are not homotopic in the punctured plane. This is the contradiction here. So to really understand how these two paths are not homotopic to each other, we need to understand three concepts. Let's start with the fundamental group, right? The fundamental group of a topological space X is the group of all loops up to homotopy within that topological space that begin and end at this little x naught. So if two loops are in a topological space are homotopic, they'll be part of the same element of the fundamental group. The operation on this group is loop concatenation. See if you can think for yourself what associativity, inverse, and identity might look like, or feel free to look them up afterwards. Now we're going to calculate this fundamental group. To do that, we're going to use the concept of a covering map, right? So what's a covering map? Well, covering maps are functions of P from two topological spaces from X to Y, such that the following two things hold, right? P is a surjective continuous map, firstly. And secondly, for every open neighborhood U in the place it's going, the pre-image of that is a disjoint union of homeomorphic copies of U. Homeomorphic just means it's continuous and its inverse is continuous. A good visualization may look something like this, like a kind of stack of pancakes type idea. You see you have this U at the bottom, and then its pre-image is a bunch of different copies of it that are homeomorphic, and this is a surjective map. Now we're also going to use this concept of lift. So what is a lift in this context? Well, since we have A naught G1 and A naught G2 going from 0, 1 to the punctured plane, and our P is a map from the complex numbers to the punctured plane, then we can find a lifting for each path starting at A naught such that the composition of P with this lifting is equal to the A naught G1 or A naught G2. If these two things end at different points, though, then these two, if the lifts end at different points, because we're making them start at the same point, then we have that these functions, the images of these aren't homotopic, which would be a contradiction that we could pull. So I claim that this is a covering map for our group, right? And let's have this E naught be a point in the complex plane such that A naught equals e to the I E naught, which we know exists, right? Because A naught is not equal to 0 and P is surjective. Now let's consider our liftings. I claim that they are these two things. One can check that, right? Indeed, that these are the composition of these functions turns out to be the functions themselves. However, note that A naught G1 of 1, right, because this is going from 0, 1 to the complex numbers, is E naught, while in the other case, we have 2 pi n plus E naught. And since we know n is not equal to 0, they have different ending points. So these paths are not homotopic, and we have a contradiction. Therefore, we can say that f has at least one root. From there, right, we can take another look at f of x. If it has one root, say x naught, then we can rewrite the polynomial as f of x equals x minus x naught times this g of x, right, which is some polynomial with complex coefficients, and this leading term. Hey, we know that has at least one root. And so from there, we can continue in this manner until we've kind of decomposed the polynomial into n linear factors. And these indicate our n roots. I want to thank, again, Matthew Steed, whose article I was using as a big basis for this. I want to thank conversations with Dr. Goins that I had, and, of course, these two little bits as well. Thank you so much, and have a wonderful break.